In 1999, there was this incredibly well-funded, high-stakes clinical trial that was, well, it was nearly thrown entirely in the garbage.
Right. And not because the drug failed.
Exactly. Not because the drug didn't work, but because a researcher ran like a standard t-test instead of an ANOVA.
Oh, yeah. A single box checked wrong on a mathematical flowchart.
Right. Millions of dollars, years of research, and, potential patient outcomes all just hanging by a thread. It's a terrifying reality for anyone who works with data.
It is a massive responsibility, honestly.
Yeah, you find yourself staring at a spreadsheet with like thousands of rows and hundreds of columns. It looks like the green falling code in the Matrix, right? And the pressure to translate all that chaos into a confident decision is just immense.
The fundamental issue there is that we are frequently taught to view statistics as just this advanced branch of mathematics.
Right.
But math is merely the engine under the hood.
Yeah.
Statistics is the steering wheel. It's the applied logic of decision-making under uncertainty.
Okay, so let's unpack this, because our mission for today's deep dive is to essentially master that steering wheel.
I love that framing.
Yeah, we're looking at this incredibly comprehensive statistics training manual. It's designed specifically for undergraduate and postgraduate projects. And what makes this framework so brilliant is its authorship.
Right, Dr. Bright Boama and Dr. Helena Ninti.
Exactly. Dr. Boama is a medical doctor and clinical toxicologist, and Dr. Ninti is a nutrition research scientist. I mean, they deal with real-world, literal life-or-death data.
Which naturally, it just strips away all the pure theory, right? It leaves you with an incredibly practical survival guide.
Yeah, they really aren't interested in making you memorize abstract proofs.
No, not at all. They outline this concrete methodology to navigate the data landscape from raw variables all the way to hypothesis testing.
Making sure you deploy the correct statistical mechanism for your specific data set. And what I found interesting is that their methodology doesn't start with complex equations. It starts with a really rigorous 5-step data wrangling workflow.
Right, the 5 steps: discovery, cleaning, structuring, enriching, and validating.
Yeah, and I feel like most people just rush straight to the analysis part.
Oh, constantly.
But if you're listening to this and looking at your own massive Excel sheet right now, ask yourself, did you actually clean the duplicates in step 2, or did you rush ahead?
Because if you skip the structuring and validation phases, well, your p-value is already lying to you.
Wow, already lying.
Yeah, I mean, the structuring phase alone dictates the validity of every subsequent test you run.
So if we connect this to the bigger picture, this workflow basically forces you to definitively classify your variables, right, before you run a single calculation.
Absolutely. Dr. Bawama and Dr. Nitti emphasize this really hard divide between categorical data.
Like nominal or ordinal groups, right? Like disease stage or gender.
Yes, exactly. So categorical data on one side and numerical data on the other.
And numerical would be like the continuous or discrete measurements, blood pressure, dosage amounts, that kind of thing.
You've got it. That classification is the absolute most important step.
I kind of see this like kitchen prep.
Okay, how so?
Well, you wouldn't take a raw, unwashed root vegetable straight from the dirt, toss it into a sauté pan, and just expect a Michelin star outcome, right?
No, definitely not.
The prep work, the washing, the very specific chopping technique, that dictates the chemical reaction in the pan.
That is a great analogy.
Oh.
If you try to feed categorical data into an engine that's designed for numerical data, you are essentially asking the computer to calculate the average of stage 1 and stage 3 cancer.
Which means absolutely nothing.
Right. It creates a mathematical hallucination. The system will often just spit out a number anyway.
And if you don't understand those underlying variable types, you might actually publish that hallucination.
Exactly. And once you have validated the integrity of your variables, you have to establish the baseline reality of your specific sample.
Which requires a deep dive into descriptive statistics, right?
Yes. Now, we all know the basic measures of central tendency, mean, median, and mode.
Right. But I want to push back on this a little bit. Why do we need all three? Isn't the average, the mean, usually enough for most projects?
Well, you would think so, but the training material highlights how violently a skewed distribution can invalidate a standard mean.
Violently skewed, huh? Give me an example.
Okay, let's say we are tracking patient recovery times, right? And 99 patients recover in 2 days.
Yeah, 2 days. That's fast.
But one patient has a severe complication and takes 80 days to recover.
Oh, wow. Yeah, that's a massive outlier.
Exactly. That single extreme right skew completely destroys the utility of the average. It pulls the mean so far to the right that your average recovery time no longer represents a single actual patient in your cohort.
Ah, I see. So nobody actually recovered in, say, 10 days, but the mean says 10 days because of that one guy.
Precisely. That is the mechanical failure of the mean in real-world data. It is highly sensitive to magnitude.
So that's where the median steps in to save the day.
Right. The median relies on position, not magnitude. By simply ordering the recovery times and selecting the physical middle value, the median completely neutralizes the impact of that 80-day outlier.
Oh, that makes so much sense. But here's where it gets really interesting to me. We don't just need to know the center of the data, right? We have to understand the chaos around the center.
The variability, yes.
Yeah.
Range, variance, standard deviation.
Yeah, but honestly, staring at variance or standard deviation outputs is often just unintuitive.
Yeah.
The authors push really hard for visual anomaly detectors.
Especially the box plot.
Right. Because pie charts and histograms are fine for frequency, but a box plot maps out the interquartile range.
Yes, the interquartile range, or IQR, it's essentially the middle 50% of your data.
So a box plot physically draws a boundary around that core 50%.
Exactly, with the whiskers extending out to capture the rest, which visually isolates any outliers. When you glance at a well-constructed box plot, you immediately understand the density and the spread of your sample.
And you don't even have to decipher the standard deviation calculations. It's just right there.
Exactly.
Okay, so our descriptive box plots look great for the, say, 50 patients in our trial. We know exactly how our sample behaved.
Right.
But if we take this to the FDA and say, look, this new protocol worked perfectly for our 50 people, the immediate response is going to be, prove to us that it will work for the next million patients.
Which is a massive logical leap.
A huge leap. How do we mathematically justify jumping from our tiny, isolated sample to the entire global population?
Well, that leap is the entire basis of inferential statistics.
Hmm.
We are inferring population-level truths based on sample-level evidence.
And to execute that leap without simply guessing, the scientific community relies on the hypothesis testing framework.
Right. The manual codifies this into a very strict 5-step procedure. Step 1 is stating your hypotheses.
Stating the null hypothesis, right? The H0 and the alternate hypothesis, the H1. I actually like to think of this as a courtroom trial.
A courtroom. I like that.
Yeah. So the null hypothesis is the defendant, right? Presumed innocent until proven guilty. It represents the boring status quo. Like, it assumes your new drug does absolutely nothing or that there is zero correlation between two variables.
That's a perfect way to conceptualize it. And then step 2 requires establishing your level of significance, your alpha.
Which is typically set at 0.05.
Almost always, yeah. Then steps 3 and 4 involve calculating your specific test statistic and extracting the p-value.
Okay, so continuing the courtroom analogy, we, the researchers, are the prosecutors. We're trying to prove the alternate hypothesis that the drug does work.
Right.
So the p-value represents the weight of the evidence against the null hypothesis. If our evidence is heavy enough, like if the p-value drops below that 0.05 threshold, we've proven our case beyond a reasonable doubt.
We reject the null hypothesis.
Okay.
Exactly. But, the mechanism of the p-value is frequently misunderstood.
Oh, how so?
It is specifically the probability of observing your data or something more extreme, assuming that the null hypothesis is entirely true.
Okay, wait, say that again?
If the status quo is true, what are the odds we'd get this exact data? If that probability is less than 5%, the scientific consensus is that the status quo assumption must be false.
Right. But I am going to push back on the strictness of this 5-step framework for a second.
Go for it.
This all assumes we always want to find a difference. But what if we are testing a generic drug against a name brand drug, and our goal is actually to prove they are exactly the same? In that case, we want the null hypothesis to survive, right?
Well, that requires a slightly different approach known as equivalence testing. But your point actually reveals a really critical vulnerability in standard hypothesis testing.
Which is?
Failing to reject the null hypothesis does not mean you have mathematically proven the null hypothesis is true.
Wait, really? It doesn't.
No, it simply means your sample didn't provide enough evidence to convict. It is a subtle but profound difference in scientific literature. Absence of evidence is not evidence of absence.
Oh, wow. Yeah, that nuance is why translating these concepts correctly is just so vital.
Absolutely.
Which kind of leads us to the actual mechanics of it all. We understand the rules of the statistical courtroom now, but when it is time to calculate that p-value, how do we actually know which formula to run?
Right, because there are dozens of tests.
Yeah. We have this massive flowchart from Dr. Boama and Dr. Nenti, and it operates like this intricate logic game.
And the entire flowchart hinges on those variable types we discussed back in the workflow stage.
The categorical versus numerical split.
Exactly. So the first major operational path is comparing means. You use this when you want to look for a mathematical difference between distinct groups.
Okay, so structurally, this requires one categorical variable to define your groups and one numerical variable to provide the actual measurement you're comparing.
Precisely.
So if my categorical variable only has two groups, let's say we are comparing numeric vitamin D levels between inpatient and outpatient care, the flowchart dictates an independent samples t-test.
Right. Two groups, one measurement, t-test.
But wait, if the t-test is just comparing means, why does the flowchart forbid us from using it if we add a third group? Like, if we have inpatient, outpatient, and ICU, why can't I just run multiple t-tests to compare them all?
That is a brilliant deduction, actually, and it gets to the absolute core of why the ANOVA exists.
The analysis of variance.
Yes, because if you run multiple t-tests across 3 more groups, you trigger something called alpha inflation.
Alpha inflation, like the 0.05 error rate inflates.
Exactly. Every time you run a t-test, you accept a 5% chance of a false positive. If you run 3 separate t-tests to compare your 3 groups, those error rates compound.
Oh, no. So suddenly your chance of a false positive jumps from 5% to, like, nearly 15%.
Right. So the math essentially starts creating phantom discoveries just because you ran the test too many times.
That is wild.
Which is precisely why we switched to the ANOVA. The ANOVA evaluates all 3 groups simultaneously in a single mathematical sweep.
Oh, I see.
It looks at the variance between the groups and compares it to the variance within the groups, holding your error rate at a strict 5%. So 3 or more groups plus 1 numeric measurement mandates in ANOVA.
Okay, got it. So if we're dealing with clinical data, often we don't have nice, clean numeric measurements, right? We just have categories.
Right, like survey responses.
Yeah, like did the patient smoke? Yes or no. Did they develop lung cancer? Yes or no. I'm assuming a t-test completely collapses there, right? Since there's no numerical mean to calculate.
So it fundamentally breaks. That scenario pushes you down the second path of the flowchart, finding associations.
When both variables are categorical.
Right. When both are categorical, you deploy the chi-squared test.
Chi-squared. Okay.
Because the chi-squared doesn't look for means at all. It compares the observed frequencies in your categories against the frequencies you would mathematically expect if the 2 variables were completely independent.
So it's essentially looking for unexpected overlaps.
Exactly. If the smoking group has a drastically higher frequency of lung cancer than the non-smoking group, the chi-squared flags that association.
Makes sense. That covers categories. But what if we strip away the groups entirely? Path 3 is when both variables are numerical, right? Continuous data. Like, we want to see how age correlates with blood pressure.
Right. For purely numerical relationships, we explore correlation and regression. A Pearson correlation coefficient will tell you the strength and the direction of the relationship on a scatter plot.
Is it a strong positive slope? A weak negative slope?
Exactly.
But correlation is just observation. If I am analyzing business operations or building predictive tech models, observation isn't enough, you know.
You need to predict.
Right, I need to forecast outcomes.
Yeah.
I need to know what happens to Y if I actively change X.
And that requires multiple regression. Instead of just observing a scatter plot, multiple regression builds a predictive mathematical equation.
Y equals A plus BX and all that.
Yes. It allows you to define a single numeric outcome, your dependent variable, and predict it using multiple independent variables simultaneously.
So what does this all mean when we get into the weeds of the math? Like, how does it juggle multiple inputs without them corrupting each other?
Well, the elegance of multiple regression lies in its ability to isolate variables.
How so?
Imagine predicting the sales revenue of a storefront, and you're basing it on the neighborhood population, the amount spent on advertising, and the square footage of the store.
Okay, 3 different numerical inputs.
Regression calculates the specific impact of your advertising spend, while mathematically holding the population and square footage perfectly constant.
Wait, really? It could just freeze the other variables?
Mathematically, yes. It strips away the confounding factors to give you the pure effect of a single variable.
That is incredibly powerful. It's almost like having a control group for every single factor in your data set.
It's essential for complex data.
Okay, so we have our primary toolkit. T-tests for 2 groups, ANOVA for 3 or more, chi-squared for pure categories, and multiple regression for numeric prediction.
Correct.
But all of these tests, the parametric test, they assume our data is behaving nicely, right? They assume it forms this beautiful, normal distribution bell curve.
Which real-world data rarely does.
Exactly. What happens when the real-world data is just a heavily skewed, chaotic mess?
If your data fails the assumptions of normality, running a parametric test like a t-test or an ANOVA will calculate a fundamentally incorrect p-value.
So you risk validating a totally false hypothesis.
Yes. So to survive messy data, the manual directs us to the deeper layers of the flowchart, the non-parametric alternatives.
I understand needing a backup plan, like a mathematical stunt double for our tests. But how do they actually work? If the numbers are so skewed that they literally break a t-test, how does a non-parametric test magically fix the chaos?
It fixes the chaos by abandoning the magnitude of the numbers entirely.
Abandoning the numbers.
Yep, it utilizes a ranking system instead.
Okay, I'm intrigued. Walk me through it.
Think back to our patient who took 80 days to recover, while everyone else took 2 days.
Right, the massive outlier.
A parametric t-test tries to use the actual number 80, which drags the mean into orbit and shatters the variance calculation. But a non-parametric test, like the Mann-Whitney U-test, it lines up all the recovery times from fastest to slowest and simply assigns them ranks.
Like first place, second place, third place.
Exactly.
Oh, wow. So the actual numerical value of 80 days gets completely erased. The patient just becomes rank 50.
Yes, the massive outlier entirely loses its disruptive mathematical weight.
That's brilliant.
It is. The non-parametric tests, the Mann-Whitney U for independent groups, the Wilcoxon for paired samples, the Kruskal-Wallis instead of a one-way ANOVA, they all calculate their p-values based on the distribution of ranks rather than the raw, skewed measurements.
Or like Spearman instead of Pearson for correlation.
Exactly. It is an incredibly robust way to find significant differences in highly unstable data.
That ranking mechanism is such a clever workaround. It just flattens the extreme values.
It saves a lot of research, honestly.
Speaking of mechanisms, I noticed the very final tier at the ANOVA section in the flowchart mentions something called post-hoc tests, like Tukey or done.
Ah, yes. The follow-up tests.
Yeah, so if the ANOVA already evaluated our 3 groups and gave us a significant p-value, why are we running another test after the fact?
Well, because the ANOVA is essentially just an alarm system.
An alarm system.
Yeah. If you test 3 different dosages of a drug, the ANOVA evaluates all of them, and if it's significant, it simply says, a mathematical difference exists somewhere within these groups.
Wait, it doesn't tell you where the difference is?
No. It doesn't tell you if dosage A is different from dosage B, or if dosage C is different from dosage A.
Oh. So it tells us a crime happened, but it doesn't point out the culprit.
That's a great way to put it. The post hoc test is the police lineup. Post hoc literally translates to after the event.
Oh,
Tests like Tukey's systematically compare every single group against every other group. And they do it while controlling for those compounding error rates we talked about earlier.
the alpha inflation.
Right. So they pinpoint exactly which specific categories are driving the statistical significance. You really cannot fully interpret an ANOVA without the follow-up post hoc analysis.
Wow. We have mapped out some incredibly dense territory today. Let's synthesize this journey a bit.
Sure.
We started with the realization that statistics isn't just crunching numbers. It requires a strict workflow of discovery and validation to ensure we don't, feed categorical groups into numerical engines.
The foundational prep work.
Right. And then we explored how the median and the Bach plot act as visual anchors against violent data skew. We stepped into the courtroom of inferential statistics, weighing the p-value evidence against the null hypothesis.
And finding the right toolkit.
Exactly. We navigated the flowchart, matching our specific variable architectures to ANOVAs, regressions, and those rank-flattening mechanisms of the non-parametric world.
And it is vital to note that Dr. Boama and Dr. Netti's comprehensive manual ultimately expects researchers to implement this entire logical framework using the statistical programming language R.
Oh, right. So you aren't calculating a Kruskal-Wallis test by hand with a pencil.
No, definitely not. You are learning how to correctly instruct the software to execute the logic you have chosen.
You just have to know how to steer the wheel.
Right.
And ensure you aren't driving the data off a cliff.
Exactly. But, before we conclude, there is an underlying current to this entire system that really warrants a closer look.
Oh, what's that?
We just spent all this time dissecting a highly logical, deeply mathematical flowchart. It feels incredibly rigid, objective, and absolute.
Yeah, very black and white.
But think back to step 2 of the hypothesis testing framework. Selecting the level of significance. Alpha equals 0.05.
The threshold for the p-value.
Right. That singular threshold dictates whether your p-value is considered statistically significant enough to reject the null hypothesis. It represents the absolute boundary between a published scientific discovery and a completely failed experiment.
Yeah, that's a lot of pressure on one number.
It is. Yet that zero point zero 0.05 threshold is not derived from a fundamental law of physics or some advanced mathematical proof.
It's not.
No, it is a completely arbitrary human convention.
Wait, really? Just arbitrary?
Yes. Early statisticians in the 1920s essentially agreed that a 1 in 20 chance of a false positive just seemed like a reasonable heuristic.
You're kidding. A heuristic.
That's all it was. And over decades, that casual heuristic just hardened into an unbreakable academic law.
Wow.
So I leave you with this to ponder. How many massive world-changing breakthroughs like revolutionary medical treatments, profound sociological patterns, crucial climate insights, how many of those have been completely abandoned by researchers and lost to history simply because their p-value landed at 0.051 instead of 0.049?
Oh my gosh. That is terrifying to think about.
It is a stark reminder that while statistics is the most powerful tool we have to understand the universe, it remains a tool bounded by the arbitrary thresholds of human consensus.
Well, on that slightly existential note, the next time you are staring at that overwhelming spreadsheet, hopefully, you can actually see the structure beneath the chaos.
The matrix code won't look so scary.
Exactly. You know your variables, you know the mechanisms of your tests, and you know how to translate raw numbers into confident reality. Thank you for joining us on this deep dive. Now get out there and test some hypotheses of your own.